Let's look at the composition now. So we looked at the different kinds of raster layers: continuous, categorical, and fuzzy. Now the composition for the simple and extended raster models. The simple raster model applies to continuous data, and the extended raster model applies to categorical data. So let's first look at the simple raster model. So the simple raster model simply describes the basic raster properties. Rasters have cells or pixels, and a cell has a resolution. And this is the very fundamental concept to raster GIS and remote sensing. The resolution of a cell tells us how large that cell is in the real world. And by knowing how large a cell is in the real world, we can then determine what types of things could be recorded in that cell. So a cell could be a square kilometer, a square meter, or even a square centimeter, millimeter, nanometer, or whatever you want to have for a cell size. But as a general idea and rule, the cell size, or what we call the detail of that can be represented by that cell size, must be sufficient for the required analysis. Determining resolution, we start with the idea that the detail must be sufficient for the required analysis. Now, for discrete object representation, as a general rule, the cell size should be 1/4 the minimum required or minimum resolvable feature that is required to be represented by the raster. Here's an example of a pool. So trying to represent a pool with different types of cell sizes. With the small cell sizes, like here, this just happens to be a 1 meter cell, and that means that a cell is 1 meter by 1 meter. And this is the reporting of a cell size in linear resolution, in linear units. So 1 meter, we have to tell ourselves that's a linear cell size, which means it's really 1 meter by 1 meter, or 1 meter squared. So resolution can be reported either as a linear cell, which is the dimension of one side of the cell, and that tells us the cell is square, or it could be represented as an area. As an area, we don't know the cells were square, but it's a good guess they are square. Or we could say 1 meter by 1 meter, or 1 meter by 2 meter if it's not square, etc. So when linear resolution is reported, we know that the cell was square. And it's a linear resolution by linear resolution, like 1 by 1 meter. So this pool at a 1 meter cell size is fairly accurate in its size, let's say. The original size is 71 square meters. Using a cell size of 1 meter, it goes up to 73. Why? Because certain cells can only be pool or not pool. And so if a cell, part of it intersects, let's just look at a cell here, and let's say this is the edge of the pool, and the edge of that pool, I'll just make it black here, happens to be encountering part of that little cell that we see here. It intersects a corner. Well, then that whole cell has to become pool. And so that leads to overrepresentation of the actual area of the pool, because now cells have area. At a 2 meter cell size, it goes down to 72, and that's, again, not generally going to be true. Just so happens with this example. At a 4 meter cell size, it goes up to 80 square meters. And the larger we go in cell size, it's likely that this number will generally increase. So if we look at a graph of cell sizes and how they increase, it might look like it might look something like this, but there could be jagged bits in there. It could go up and down, but the overall trend will be increasing. So the size of cells will increase the size of a feature in the real world as those cells get larger. So in summary, resolution or cell size is fundamental, and smaller size cells provide more detailed rasters, higher resolution, higher spatial accuracy, but a drawback is there's slower display and processing. So if we have more cells, things will be slower when we do operations with those rasters in the computer. The file sizes will also be larger because of the greater number of cells. So there's advantages and disadvantages to a smaller cell size. And sometimes, as I said, the rule is that the cell size must be sufficient for the required analysis. So you may end up with a very large file size and slow processing speeds because of that. Larger cell sizes, advantages, less, well, disadvantages we could say. One disadvantage is less information. So there's less cells to deal with because of the lower resolution. That means as well lower spatial accuracy. So those are disadvantages of a large cell size. The advantages are faster display and processing, smaller file size, as well as the drawback of subtle patterns or objects being obscured or missing altogether from the representation. All rasters are made up of rows and columns. Columns are vertical and rows are horizontal. Where a column and row intersect, we have a cell value. And value here does not connote a numeric meaning or non-numeric meaning. It's simply what is recorded in the cell. So don't get the term value confused with number in the context of a raster layer. So numbers are always used, but not all numbers have numeric meaning. So we call it a value that is there. The value can represent something numeric, continuous, or something categorical. And of course, columns and rows are just like in a spreadsheet, and that makes the raster equivalent to a numeric array, which computers are very fast at processing. Within GIS and remote sensing, all rasters have two coordinate systems. The first one we just saw, which is the column row or cell address coordinate system. That's internal to the raster and never changes. Whereas to line that up or line that raster up with things in the real world, we also have a projected or real world coordinate system associated with the raster. And the origin of these two things are different in different locations. So the 0 column, 0 row, or 0, cell, we call that cell 0, is always in the top left-hand corner of the raster. And because of that, row values increase downwards. So the bottom of the raster has the largest row value. Likewise, from the top left corner, row or cell 0, our columns increase towards the right, just like the number line. Now, when that raster is put into the real world through a process of registration or otherwise, then we have a real world system, and that real world coordinate system will have a origin, which is where the two x and y axes of the number line represent, or intersect, I should say. So 0 is right there. So the x and y axes of a real world coordinate system are always going to be somewhere either at or beyond the bottom left corner of the raster. And that means that the smallest Cartesian coordinates for a raster layer will always belong to the cell with the largest row value and smallest column value in the column row address system. And that's the bottom left-hand cell. The corner of that has the smallest projected coordinates when a raster is in a real-world coordinate system. Whereas the smallest column row is always going to be up in the upper left corner of the raster. As I mentioned, values are in cells, and values can be integers or they can be real numbers. And it's up to us to know whether that value means a number or it means a difference of kind, a category or categorical raster. And we have to know that because not all operations in a GIS are going to be appropriate for both of those things. And the computer won't tell us that we're doing something wrong. We must know it. So you must know always whether the numbers represent categories or differences of kind, or are they real number continuous values. In most GIS systems, including ArcGIS, we have the ability to have cells that have no value in them, and these are called no data cells. Here they're represented just by some color. In ArcGIS, they will be transparent by default. So you don't see them, but they're still there and they contain an actual value. That value is something that is either just outside of or at the maximum or minimum value for the data type that's used to represent the raster. Not type of data, but data type, which is slightly different. We'll talk about that when we look at the properties of the raster. So let's look at the extended raster model now. The extended raster model is just an extension of the simple raster model, and it includes all of the properties we just saw in the simple raster model. So the extended raster model allows for multiple thematic layers or data to be assigned to each grid cell or raster cell. By the way, a grid is just another word for a raster. So some people will use them interchangeably. That being said, the extended raster model only applies to integer level data types in ArcGIS Pro, because integer level rasters can have attribute tables, and they're called a VAT or RAT. Raster attribute table. VAT values attribute table. So those two acronyms are used for the attribute table that goes along with any integer level data type raster in ArcGIS Pro. And inside of that value or RAT or VAT, the attribute table, we see values, and the values are the cell values. And again, for categorical data, those cell values simply signify a difference of kind is being observed within the raster cells. 1 is different from 2, 4 is different from 2, 3 is different from 1, 5 is different from 4, 3, 2, or 1. And there's no inequality here. Again, these numbers are just labels. So they're just labels. And 5 is not greater than 2 if it's just a label, it's just different. 3 is not greater than 1, and 4 is not greater than 3. These are just labels. So I cannot stress that enough. You must understand that concept. So with each value, all cells with a particular value belong to the same zone within the extended raster model. So zones are simply one category. So a category is called a zone in the extended raster model. And therefore, for each zone, we can have multiple attributes, such as how many cells are part of that zone. If it's a thematic raster, categorical raster, which by definition they would be, a categorical raster is a thematic raster. So we would have the theme here, let's say a forest. So that could be maple dominant. So all value 1s represent forest, which is maple dominant, canopy, 30% of the canopy making up, and 8% bug damaged, for example. So we can have multiple attributes assigned to each category or zone within the extended raster model. So again, integer grids can have a value attribute table or raster attribute table. So those are interchangeably used in terminology for attribute tables that belong to rasters. And they have to be a categorical layer to be interpreted as a raster attribute table or values attribute table. Floating point data types, rasters or grids, don't have value attribute tables. Now this can be confusing for some people because you might see that an attribute table is available for a thematic layer which is continuous. And that is true if that thematic layer was in fact storing values as integers. So an integer level raster, again, can be used for the representation of any numbers. So a continuous variable could use integers. And if so, it will have a value attribute table, but that has no meaning at all in terms of interpretation. The value attribute table simply tells us the cell values themselves. Whereas floating point, and again, floating points are belonging to the set of real numbers. Those are things with decimals like 1.42 or 0.37 or negative 0.21, etc. And that can also be stored in cells. And that type of data, when stored in cells, must be in what's called a floating point raster data type. And because of that, there is never an attribute table for that type of data. So zones are any two, or any cell, in fact, that has a value in a categorical layer. And generally, two or more cells with the same value comprise a zone. But it could be possible to have a zone that's just a single cell. And generally, though, a zone of contiguous cells represents usually a single feature. Here, for example, in this illustration, we have zone 2. That means all those cells have a value 2, and there are two disjunct regions to that zone. And 4, for example, there's also a zone 4. And it has 3 disjunct regions comprising it. Zones are important to understand because they relate to zonal functions in raster, which we'll see later on in the course. That is, operations that operate on zones as a single logical entity. As I alluded to previously on this slide we just talked about, regions also exist. So regions are simply groups of cells or cells that are disjunct from each other. So in this case, zone 2 has 2 regions, 1 and 2 right there. So we say zone 2 has 2 regions. Zone 1, well, there's a lot of 1s on there. And we might say these two are part of the same zone if they're touching by a corner or sharing a border. So that could be 1, 2, 3, 4, 5 regions. So there are 5 regions comprising zone 1. And so a zonal operation in raster would use or do something to all of those cells with a value 1, no matter where they are within the space that we are looking at, the spatial domain of interest. So zones and regions. Why are regions important? Well, there are functions that operate on regions of zones. And we'll see those later on in the course.